Buffon's needle is one of the first and most famous problems in geometric probability. The problem was first introduced in 1777 by a French mathematician, Comte de Buffon, and the idea was supposedly inspired by a popular French gambling game, which translates to the game of fair square. A player must toss a coin onto a grid of squares, and if the coin touches any side of the square, the player loses. Buffon asked what is the probability of winning this game, and its solution serves as a good warm-up to his actual problem. Suppose the square has side length s and the coin has radius r. The coin is now tracing out a path where the coin is tangent to the sides of the square, and the player just barely loses. As long as the coin's center falls within the area being traced out, the player wins. The inner square has side length s minus 2r, and the probability of landing within the inner square is just its area divided by the total area. This simplifies to 1 minus 2r over s all squared. This concept of dividing the measure of the favorable region, the inner square, by the measure of the total region is the essence of geometric probability, and we can use it in Buffon's needle problem. Suppose you have a grid of parallel lines with a distance d between them. The problem asks if you throw needles of length L, what is the probability that a needle crosses a line? Focusing in on two lines, we can see that the probability is approximately 1/3. And to find the exact probability as a function of the length L and distance d, we need to consider the two random variables which determine if the needle crosses a line: its position relative to the lines, meaning how far up or down it fell, and the angle theta it forms with the horizontal. These two random variables are what make the problem difficult. However, there's a clever way to eliminate one. Instead of asking what is the probability of a needle crossing a line, ask what is the probability of a line crossing a needle. These questions are the same since the needle moving up or down is the same as a line moving down or up, just from a different reference frame. Looking at some specific angle of theta, this frame removes the variable of how far up or down the needle fell. And using the concepts of geometric probability from the warm-up, the probability of a line crossing a needle is simply the height of the needle, L sine theta, divided by the total length of the region, d. But we aren't done yet. To get the solution only in terms of the constants, L and d, we need to find the average value of this probability function over all angles theta, from 0 to 2 pi. Evaluating the average value integral, we can see that the probability of a needle crossing a line is 0. The reason we get 0 is because sine theta is negative on the interval from pi to 2 pi, but probabilities can't be negative. Instead, we need to find the average value of L over d times the absolute value of sine theta from 0 to 2 pi. This is the same as the average value of L sine theta over d from 0 to pi. Evaluating the integral gives us a probability of a randomly thrown needle crossing a line as 2L over pi d. This solution is one of those weird examples where pi shows up, since there's no obvious circle in the problem. However, if we look deeper, the intrinsic circle is formed by the fact that the line can be rotated any angle theta, tracing out a circle. Mathematicians like this problem since it gives us a way to approximate pi using a simulation. This type of simulation, where randomness is used to find some numerical value, is called a Monte Carlo simulation, and it's an elegant way to approximate pi. But this is just the surface of Buffon's needle. If we graph our solution, we can see that after a certain point, the probability function becomes greater than 1, which is impossible. This means we made some underlying assumption during the problem. If L were greater than d, then above some critical angle, theta c, L sine theta c would be greater than the distance d, meaning the probability function would be greater than 1. To get around this, we need to split the problem into two parts. If theta is less than or greater than the critical angle. If theta is larger than theta c, then we can say that the probability of crossing is exactly 1. Otherwise, we can use the probability function from earlier. This gives us a piecewise definition for our probability function. We can now find the average value of our function like earlier. However, I'm evaluating from 0 to pi over 2 for simplicity. The average value of a piecewise is found by adding the integrals of each branch, evaluated at their specific intervals, and dividing by the length of the total interval. To remove the critical angle from this final solution, we can use trig to find that theta c equals the inverse sine of d over L, and the cosine of theta c is the square root of L squared minus d squared all over L. Substituting this into our final solution gives us a generalized solution for a probability function. Graphing this function shows that as L gets bigger, the probability approaches 1. But we can generalize the problem further in what's called Buffon's Noodle problem. To start, we need some background information. The expected value of an event is defined as the sum of each value times the probability of that value occurring. For example, the expected value of a needle crossing a line when L is less than d is just 2L over pi d times 1 crossing, since the probability of 2 or 3 crossings occurring is 0. An important yet counterintuitive property of expected value is called the linearity of expectation. This states that the expected value of x plus y for some random variables x and y is equivalent to the expected value of x plus the expected value of y. The counterintuitive part is that this holds true regardless of whether or not the variables x and y are independent. Now we can take a look at the problem. Instead of dropping a straight needle onto lines, we can drop a noodle, which can be any random curve. Instead of asking what the probability of a noodle crossing a line is, we can ask what is the expected number of crossings. The only assumption we have to make is that the noodle is piecewise linear, meaning we can split it up into these tiny tangent lines. By the linearity of expectation, the expected number of crossings for our noodle is equivalent to the sum of the expected number of crossings for each tiny tangent line, which we can say is infinitely small. Since we just showed that the expected number of crossings for any needle where L is less than d is 2L over pi d, we can apply this to our tangent lines, which have length x. Factoring out the constants and seeing that x1 plus x2 and so on is equivalent to L, we can see that the expected number of crossings for the noodle is 2L over pi d, no matter how long it is, and regardless of the shape. Despite the complexity of the problem, we were able to find an elegant solution. However, there's an even nicer way to find the solution, which leads to another discovery. Since we know that the expected number of crossings is a function of the length, we can write it as some constant times the length, where we pretend to not know that the constant is 2 over pi d. If we had some shape where we knew the expected number of crossings as well as its length, we could solve for c. A circle with diameter d will have exactly 2 crossings, no matter what angle and where it falls. And its length, or its perimeter, is simply 2 pi r, or pi times d. Solving for the constant, we can see that c equals 2 over pi d. However, what was unique about choosing a circle? If we had any shape that fits perfectly between the lines no matter what angle it falls at, we would know that the expected number of crossings is 2. A curve like this is called a curve of constant width, meaning that the distance between any two opposite points is constant. A famous example of this is a row-low triangle, which is formed by connecting the arcs centered at the vertices of an equilateral triangle. And this can be converted into any row-low polygon by simply adding sides to the triangle. And a circle could be thought of as an infinitely sided row-low polygon. Since we know the constant c and the expected number of crossings is still 2, we could solve for the perimeter of this row-low triangle. The perimeter of this triangle, or any curve of constant width, is simply pi times d. And this is Barbier's theorem, which gives us the perimeter of any curve of constant width, which can be proven using this Buffon's Noodle approach. In conclusion, we solved Buffon's Noodle problem using a creative trick We then generalized it to Buffon's Noodle and solved it using a counterintuitive yet elegant method, and extended this to proving Barbier's theorem, which allows us to find the perimeter of any curve of constant width, no matter what it looks like.